Welcome to Physics 360. We're going to go over Chapter 3, Section 4 and 6 again, specifically concentrating on what's called the quality factor and driven harmonic oscillators. Alright, so energy in an oscillator. Well, energy again is you have your kinetic and your potential energy terms. So, and what we're trying to do is figure out how they change. So how they change in time. So we're going to take the derivative of our energy and we get this term. So now we're going to factor out this derivative of position right here and get this expression. The reason why is we're going to pay attention to this term, because if you have a non-driven oscillator, we can rewrite this equation this way, and so this term and this term are equivalent, and we're going to replace it with this. So the rate of change of energy in a damped harmonic oscillator is this, and so we'll write it as this. It's minus C, that's the damping constant. What is this velocity quality factor? It's basically a characteristic used to rate the energy loss in a weakly damped oscillator. It's this symbol is a Q, and by definition it's 2 pi times the energy stored in the oscillator divided by the energy lost in one period. So how do we find this? Well, this is our solution for the damped oscillator, and so what we're going to do is we're going to apply this idea and try to figure out what this term is going to be. So we're going to need to take the derivative of our solution, and to do that you get this term, and then what I need to do is to find my change in energy over one period. I need to integrate over the change in energy with respect to time, and if I do that, I can change it into this integral, and now I need to plug in this term. So what I do is I get this expression. We can actually integrate this if we apply a substitution method, and what I'm going to substitute is this term, and that gives me this du and dt, and if I plug in my substitutions I get this integral. Now to do this integral, it looks difficult, but we're going to apply a little trick here. Since gamma is small, it's a weakly damped oscillator, we're going to say it's small, then this term right here, this e to the minus gamma t, it's not going to change that much over one period, okay? And now if we do that, that's kind of a constant, and then this integral becomes much easier to do, and so what we're going to do Alright, so if we do that, we get this expression right here for our change in energy, and we're going to do some substitutions for some of these terms in here and simplify. So this is what the damped angular frequency is, and then gamma is related to C over M in this way. So if we plug in these substitutions, we get this expression. Now with that expression, what I can do is I'm going to plug in this time constant. So gamma is equal to this particular time constant, where this tau is a particular time constant for our system. If we plug that in there, then I get this representation for my change in energy, or the absolute value of the change in energy. And then this is the total energy of the system. So now I can find the change in energy over the total energy. And if you do that, you come up with this representation. Well, why do I need to do that? Well, by definition, Q is this, right? 2 pi times the energy stored in the system divided by the change in energy over one period. And I take this substitution, plug it back in here, and I get this representation for Q, or the quality factor. And then plugging in some definitions for the damped period and what tau is, you can represent Q in these terms. And that's the quality factor. Now, what is a driven damped oscillator? Well, you've got your right here, your Newton's second law expression. There's the force caused by the spring. Here's the drag force. And then here's the driving force. We're going to drive it with a sinusoidal force, or some force, in this format. And if we do that, this is what's called as a damped driven oscillator. We can rewrite it this way, and so it becomes basically a second order differential equation with a non-homogeneous part right here, and we can solve that quite easily. The way the textbook solves it is we want to look at two cases. We want to look at a case where there's no damping, but it's still driven, and one where there's with damping and it's driven. So we're going to look at the no damping case first, which gives you this system. So we're going to claim that as our standard solution for our oscillator is this, and then we're going to plug it back in, take its second derivative, group everything together, and if we do that, we get this expression. Well, if you look at this expression, you got a cosine omega t here, and you got this particle, but there's got this phase difference. So when is this actually true? It only has two cases where the solution works: if the phase is equal to 0, or if the phase is equal to pi. So we have two solutions. So let's try the phase is equal to 0. If the phase is equal to 0, this is our equation. The cosines cancel, and I can solve for the amplitude of my oscillator is this. And then if we rework this system, factor out an m, we can write the change in amplitude as this. Now, the important person is this term right here. If our driving frequency here, omega, gets close to our resonance frequency, this term gets small, and so the amplitude gets large, and this is what you would refer to as resonance. So you get a very large amplitude if your driving frequency and your resonant and your natural frequency are equivalent. So the other solution is pi. So if we plug pi in here, the cosine term here, if we subtract off a phase difference of pi, is equivalent to this, so they cancel. We get this term here, except the problem is this is equal to -1 in this case, and so you get this minus sign. It's different than up here. There's this extra minus sign, and then you do your simplification again, and you can see how the bottom here is a little bit different from a sine. But again, when the driving frequency gets very close to the natural frequency of the system, this number gets small, so A gets very large, and that's what we refer to as a condition called resonance. And usually any driven system, you don't want that. If you don't want maximum amplitude, like a bridge, you don't want it to resonate very far out of place, or strange things happen, or a building the same way. At the actual damped case, so here's our standard differential equation that we're dealing with of our system. There is the acceleration term, the drag term, and the spring force term, and then here's our driving force term. Now we're going to represent this a little bit differently. I'm going to represent this cosine term over here as an exponential, an imaginary exponential, because this is the I for the imaginary number. I can do this by applying Euler's formula right here. So I'm going to claim that's our driving force in this case. So if we do that, then our solution to our differential equation, I'm going to write it as an imaginary exponential term also. And so now I got to plug it back into my equation and then do a lot of derivatives, a lot of simplification, grouping terms together. And when you do this, you'll find out that you can narrow it down to this expression. The e to the I omega t is on both sides, and so you basically can cancel it out, and you're left with this imaginary term. How did this get over here? Because over here was on the left-hand side. Well, you remember there's a minus sign here, and if you bring that over to this side, it becomes positive. So if I do that, and then these are the coefficients that are left after eliminating all these terms. So what I want to do is use the Euler's equation right here, and then I'm going to group. See, I have a real term here. There's no imaginary numbers here, but I have an imaginary number here. This is a real term. This is a real term. This is an imaginary term. So what I want to do is group these together. So here is our real terms right here. Here is our imaginary terms right here. And now this gives me a system to find our phase shift and our amplitude. So I'm going to arrange these terms here to make them tangent phi. And then this gives me a way of determining my phase shift that can go on depending on all the parameters of our system, our driving force, our damping constant, our mass, and our spring constant. And then I need to figure out the amplitude A, and the way I get that is if I square both these equations and add them together, then and factor out F0, I can get this expression. That should be squared here. I'm sorry about that. That should be squared. And then if I solve for A0 or A, I get this expression in terms of the omegas. And then again, if you can see this term right here, again, this is negative, this is positive, so there's a chance of this becoming small and the amplitude getting larger at that point because the denominator is smaller. So you can get a peak in the amplitude, but you don't get the same problem we had with the non-damped one where you can get really huge amplitudes. But this amplitude can grow. And that's the finish of our damped driven oscillators. We're going to be doing this in a tutorial coming up on Tuesday. So see you then.